All right, so we're going to attempt to model the addition of subtraction. In order to model something like that, we need to state, well, what does it mean to be a fraction, and what does it mean to add? Well, we came up with a bunch of ways for fractions. I'm just going to pick one. I'm going to say a fraction is an equal part of a whole area.
This is 6.2?
Yep, 6.2. And I'm choosing this one because I'm going to draw pictures of what it means to add a fraction, and my pictures look like areas. Two kinds of pictures we can draw, among many others. Circles are very popular when talking about fractions, but sometimes they're hard to draw. Squares or rectangles are easier to draw, so that's my preference. So for me, I think a cake is better than a pie for drawing fractions. So here would be half, say, to the best of my ability there. And I could do a similar half over there. And I find that drawing thirds of a cake is easier than making thirds on a pie. There's multiple approaches. So these are just two different representations of a half as an area. In a little bit, we'll actually broaden our shapes and talk about maybe a whole is a hexagon, or maybe a whole is a trapezoid. So the whole can be anything you want it to be. All right, what does addition mean? Addition means combine and count. All right, so we're going to take these area things, we're going to try to combine them and count them. So let's start with about the simplest pair of fractions we can, 1/2 plus 1/3. I'm going to draw them each as cakes, so I'm going to draw my best square underneath the half. I'm going to cut 1/2 vertically, and then I get to pick 1/2 as the one that I'm going to work on. And then third, I'm going to draw the same size cake to the best of my artistic ability. But this time I'm going to cut it horizontally into thirds, into your best guess as to where those thirds live. And then pick one of those thirds to represent that 1/3. All right, so the answer is 2. I got 2 pieces of cake. Yeah.
I thought we had to have a common denominator.
Why do you have to have a common denominator?
Because that's what the book said when I read it.
Because the book said, all right, so we got to figure out why we need a common denominator. Well, are these 2 pieces of cake the same size?
No.
No. So if I cut these and I said, hey, I get the 1/2 and you get the 1/3, if it's cake, you might argue with that, right? That's not fair. Okay. So important part about what it means to be a fraction is it's going to be equal parts of a whole, and those aren't equal parts. So. And when I'm counting stuff, would it make sense to count the chairs in this room and the people and say there's 33 of them? That doesn't make any sense, right? So same idea here. When you count, you're counting a type of thing. Right? I'm counting people or I'm counting chairs. Otherwise, I have to say just count things, and you guys get to do things, which is weird. Trick. Recut the cakes. Cut each cake like the other. So I'm going to pick a new color. So I'm going to take the thirds cake and cut it in half vertically like the other one. And I'm going to take the half cake and I'm going to cut it in thirds horizontally like the other cake. Now, what can I say here? Well, I do have a bunch of pieces that are all now the same size. In the first cake, how many pieces do I have? 3 pieces, and each piece is a 1/6. We talked about that the other day. What does the numerator mean versus the denominator? So the numerator is just a count, right, of how many I have. The denominator is what then?
The whole.
It's a description of the thing I have. I have one what? A half is what I have. Here I have one what? A third is what I have. So the denominator is just a description. And a third is a different thing than a half. Now I have a new count because I have a new description. On the other cake, instead of calling it a third, I can give it an equivalent name of 2/6. True? Okay, so now I have the same kind of thing, so I can count them up. How many pieces do I have altogether? There's 5 pieces, and they just happen to be 6. So one thing that's important with fractions is to remember the numerator has a special meaning. That's a count. The denominator has a special meaning. That's a description of what I've counted. In order to count things up, to get a total, they have to have the same description. That's why we need a common denominator, because we can only count like things.
So how come you don't count 6 and 6? Is it just because they have to stay even?
So how many pieces are over here?
Same.
No. How many pieces do I actually have?
3.
I have 3 of them. How would you describe this piece? How big is that piece? It's 1/6 of the whole. How big is this piece? Of the whole. And this one? And this one? And this one. So I have 5 things, and each of those things is what part of the whole? 1/6 of the whole. Yeah. So the denominator stays the same. That's the whole point. All we've done is give it a new name, a new description. So this is a physical model. What does a model mean? A model has to say, okay, what are the things you're adding? Well, they're equal parts of a whole. Is the word equal important there? It's super important. What are we doing with those things? We're adding them. That means combining counts. We can only do that if they have the same description. Otherwise, we can't count them up. There's one of one thing and one of a different thing. All right, let's try another one. Let's suppose we had 2/3 and 1/4. I'm going to do it just like I did before. I'm going to draw a square to the best of my ability for a whole, and I'm going to split it into thirds. And I like to make one version vertical, the other one horizontal. That helps me add them better. And I'm interested in 2 of these. So maybe this is one of my thirds, and this one is the other third. I need to show 1/4, same size whole, best of your ability. The other one, you can split in half and then half again, and then pick one of those, doesn't matter which one, to be your 1/4. What are we doing with these things again? Combining them, right? But the problem is a third is a different size thing than a fourth, so I need a common description. So we cut each cake like the other. So cut the fourths into thirds, cut the thirds into fourths. So let's see, it looks like I have a 2x4 region here. So there's 8 pieces there. Out of 3 times 4 is 12. So 3 2/3 is also 8/12. Over here, I have a 1x3 region, and the whole thing is 4x3, so I have 3/12. What does the denominator represent again? What is it?
The whole.
How many pieces are in a whole? It's a description of the pieces. So what kinds of things am I adding up here? I'm adding 12ths. How many 12ths do I have? I have 11 of them. Now I couldn't redraw this picture by putting them all into a new pan together. Room for that. So I could say altogether this is equal to one new cake. And let's see, we got thirds that way. Oops, draw that in the right spot. That looks like a third. We got fourths going this way. And then I just go pick up the pieces over here and stick them over there. So there's, from the first one, 1, 2, 3, 4, 5, 6, 7, 8. And from the other one, I'm going to throw in 1, 2, 3. So I can rebuild it to show that all those results in the same cake if we need to. So this model of what a fraction means and what addition means shows us why we have to have a common denominator. So it's that pen. We have to have a common denominator. Otherwise, we can't count because we don't have equal parts. Fractions are equal parts in the whole. All right, your turn. You get to do another. What's up?
Are they always going to be in lowest terms? When
No.
you add? No.
You could have fractions that aren't lowest terms and you could add them. And that's another layer of complication. We're not going to worry about that yet. All right, actually, let's do another one together and then I'll give you guys one to try in your own. Suppose we had 1/2 plus 1/6. We'll do this two different ways. First way is to just draw your half in one direction. Draw your 6 going the other way, roughly the same size hole. So in 6. You cut it in half, and then cut each half in thirds. I believe they're all the same size. And I just want one up here. This one up here today. So a problem like before, they're not the same size, so we'll take that trick where we just cut each cake like the other. It's wrong. It's not a pen. How that'll work anyway. Cut that one in half. It's not gonna work. Cut the other one in 6. So let's see, it looks like 1/2 could be written as 6 out of 12.
12.
And 1/6 could be written as 2 out of 12. And altogether, how many 12s do I have?
12.
We have 8 of them. Okay, so the next thing I want you to do is rebuild those 8 12s into a new hole. So redraw a hole, do the same. All right, so let's see. I have this one, maybe this one, that one, that one, that one, and that one, and then I need 2 more. Could you regroup these pieces, like consolidate them a bit?
Probably.
Like,
Well, can't you
I
reduce?
see groups of 2 up here. Right? Here's a group of 2, 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 blank group of 2, blank group of 2. So what does that regrouping give me as a new answer? 1, 2, 3, 4 shaded pieces out of how many in a hole?
6.
Okay, so I could say this is 4, 6.
But that reduces 2.
Is there another way I could do this? I could do groups of, not 2, but I could do groups of 4 instead.
4.
Yeah. So let's see, I'm going to use maybe a yellow highlighter this time. So I could say let's grab these 4 right here, and then those 4 right there, and those 4 right there. So another way I could state this answer would be to say I have 2 shaded pieces out of 1, 2, 3 groups of 4. So 2/3 would be another way to state the answer.
Couldn't you figure that out a lot simpler than regrouping?
How?
Well, if you know you have 4/6, they're both even numbers divided by 2, top and bottom by 2.
Okay, so for some kids, it's going to be easier to physically group the objects, and for other kids, they're going to just look at that as, hey, I'm going to divide. Let's go to this one right here. I'm just going to divide top and bottom by 2. Right, some kids are fine doing that. Other kids are really struggling with that idea. So it's good to have the picture version of it too, to build, to say, hey, isn't division looking for groups of 2? And you can make that connection for division means groups of 2, which means divide by 2 to get from here to there. Yeah. So here's a catch. Now you guys already knew how to add fractions, right? I'm not teaching you anything new really. Is this the way you would have done that problem, or have you done it a different way? You would have done it a different way, right? So forget about the picture for a minute. Let's just look at the problem 1/2 plus 1/6. What technique would you apply? Jack, what'd you do?
Well, 2 is a factor of 6.
2 goes into 6.
To multiply 2 by 3, divided by 3.
So 6 divided by 2 is equal to 3. So that made you want to multiply by 3 top and bottom here to make an equivalent fraction. So now you have 3/6 plus 1/6, which is a common description, right? So you happen to find in the 6 the greatest common factor, or sorry, lowest common multiple. Backwards. The lowest common multiple of 2 and 6. Right? That's a technique that's taught. And we'll go over that in more detail in a little bit. Okay, so now that is the smallest denominator I can get away with, true? I can't go smaller than 6, because does 1/6 reduce? No, it doesn't reduce. 6 is the smallest denominator possible here. All right, 3/6 plus 1/6 is?
4/6.
And even though I have the smallest denominator, I still have to reduce. So just because you went through the work of finding the smallest denominator doesn't mean you're out of the woods. You still might have to reduce. That reduces to 2/3. So the common way to teach addition to fractions is to say you have to find the lowest common multiple of the denominators, usually called the lowest common denominator. And then from there, you got to figure out how to adjust each fraction. Right? So I'm going to show you 2 different methods for adding fractions. We'll talk about the pros and cons of it. So even though I had the lowest common denominator there, I still had to reduce. Here, I didn't have to think so much about finding a denominator. 2 times 6 is 12. That was pretty straightforward. Okay. I had to do a little more reducing, one more step reducing, but I didn't have to worry about finding the lowest common denominator. Pros and cons. Okay, let's do another one. So I want you to draw a picture for me, and then we'll talk about algorithms. Can you show me 1/5 plus 1/2? Let's make it 2/5 plus 1/2. Make it more interesting. So draw a picture so that you can illustrate and explain the answer. You did it totally different?
Well, I drew it all out, but I mean to get the numbers.
Yeah. So when you're drawing a picture, there's a couple things you want to consider. You want to try to make each hole as like as you can, relatively the same size. Some days I'm really good at that, some days I'm not. Looking back at this one looks a little bigger than that one. So are some kids going to struggle with drawing these? Absolutely. How can we equalize that? Answer, paper folding. Solves that a little bit, because a piece of paper is the same size for everybody. Right? So you could take a piece of paper, fold one paper in half, shade the half. Folding a piece of paper in fifths, that's a little tricky, but you know, trial and error, you can play around. Are there some numbers you probably don't want to do with kids? Yeah, I don't think I want to fold a paper in ninths with a bunch of kids. You know, that might not go well. So you know, you pick small numbers because we're working our way up to it. Otherwise, toys that you hold on to are a good way to go. So we're going to look at that toys in a minute. But first, we got to talk about a couple of algorithms. Yeah.
Damien's class learned with Legos.
Yeah, Legos are anything that you can put together, you can make into a fraction toy. Yeah. All right, so hopefully your work looks something like this. Now, in the future, there's going to be a test on this, in which case, not only do I want pictures, but I want some explanation. I use two colors here to try and illustrate my first cut and my second cut. Sometimes that's hard. You might want to draw more than one picture. Explain what you're doing. Like I'm cutting each cake like the other, and then down here I'm combining and counting. And then if you put them together into a whole, you can see if it reduces at all. Now, you guys are fraction experts. You can look at a fraction and say, I don't think that's reduced, right? And you mess around with it. Others you look at and you're like, I'm sure that's reduced. Just because you guys have way more experience than kids. But then we can come over here and say, is there a way to try and bunch these up so we have division in whole groups? Can I do groups of 2 here?
Be a remainder.
Yeah, there's an extra one there, so I couldn't do groups of 2. Could I do groups of 3? With the shaded ones, but not the unshaded, right? Yeah, so we play around a little bit, we find there's no way to group them so that both the numerator and the denominator are happy. And that has to happen. Okay, so we're going to go over 2 different algorithms next, and then a subtraction. So algorithms, we just did a model for fraction addition. So that model actually leads to an algorithm. So I'm going to use, let's say, 2/3 and 1/2 as an example. When we built physically 2/3 and 1/2, we realized that 1/3 is a different size thing than 1/2. They didn't have the same description, so they were hard to count. So what was the first thing we did? Well, we cut each cake like the other. What does that mean? That means the thirds got cut in half, and the halves got cut in third, and altogether each cake now had 6 pieces. 2 times 3 is 6. Now, didn't these 2 pieces in the 2/3, didn't those get cut in half too?
Yeah, which you did about
So that 2 got cut in half, so now it's 4 pieces. And this 1, didn't it get chopped up too? It got chopped into 3 pieces. 3 times 1 is 3. This is a fraction addition algorithm. It's called the arrow algorithm. Answer, 4 plus 3 is 7 over 6.
Isn't that just like cross multiplication?
Sort of. We have to find a new denominator to go with it. Yes, but it's related to cross multiplication. There is a cross multiplying happening there. This is a nice, fast, easy way to add fractions. So lots of college students I've met who've struggled to add fractions all their life, I show them this and they were like, oh, it's not a problem anymore. I can see that pattern, give me any pair of fractions, I can add them. Now, downside, this does not find the lowest common denominator. Right? For example, if I use that on 1/2 plus 1/6, the arrow algorithm says, hey, just make 12 the denominator. Cross multiply 6 times 1, 2 times 1, add those new numbers up, and you get 8/12. But it's fast to get an answer. You don't have to fiddle around with what divides what and what do I multiply by what before you can even do the addition. So we'll look at the other method in a moment. Turns out it doesn't matter whether you're adding or subtracting. So suppose I had, and then right, we would reduce this. Eventually we'd realize, hey, 4 goes into top and bottom. So that would be 2/3. So let's try a new problem. Let's suppose we had subtraction, 2/3 minus 1/2. Arrow method works just fine here too. 3 times 2 is 6. 2 times 2 is 4. 3 times 1 is 3. The only difference here is what am I doing instead of adding?
Subtract.
So just put a subtraction up top to remind yourself the answer must be 1/6. Which, based on the problem above, does that make sense? If 1/2 plus 1/6 is 2/3, shouldn't 2/3 minus 1/2 be 1/6? Right? Those are part of the same fact family. Yeah. So the arrow algorithm works whether you're adding or subtraction. Same with the pictures. We'll do a subtraction picture in a minute. Yes, Sarah?
What about mixed numbers?
We'll get there in a moment. Mixed numbers are a pain in the bottom. And I'll explain why. All right, so that's one algorithm. Other algorithm. The LCD algorithm. LCD stands for lowest common denominator. Okay, so let's pick, how about 5/12 plus 1 1/15. Let's do that. Okay, so lowest common denominator algorithm says step 1, find the lowest common multiple of 12 and 15. What's the smallest number that they both go into? No, that's divisor.
Oh.
We need a number that both 12 and 15 go into, a multiple of 12. So for example, 24, 36. Does 15 go into 24?
60.
60, how did you come up with 60?
Because I know that for 15 to go into it, it's either going to have to end in a 5 or a 0.
Okay,
And so I thought through 12, and I know when you have multiples of 12, it can't end in a 5. So
so it's got to end in a 0.
0.
So,
And 60 is the closest 0 that fits 12.
okay, so you were thinking about both multiples, divisors, and you were thinking mixing those together. Okay, so excellent. Other techniques we learned back in chapter 4? How did we find lowest common
Factor tree.
multiples? Factor tree would be one way. So I can factor 12, say 12 is 2 times 6, 6 is 2 times 3. 15, on the other hand, is just 3 times 5. So the LCM, according to 12, has to have a 2 in it, has to have another 2 in it, and it has to have a 3. Right? That's what 12 says. What does 15 say? 15 says I need a 3, but we already got it, so I just need a 5. And if you multiply those together, you will definitely get 60. So somehow, whatever method you choose, you've got to find the lowest common multiple of the two numbers. And we came up with a bunch of techniques to do it before. You can mix and match those like Lizzie did. All right, so now what we know is we need to rewrite this as some number of 60ths and some number of 60ths. So step 2 is to figure out how to get to 60. So essentially what I have to do is say, okay, well, 12 goes into 60 5 times. So I'm going to have to multiply 5 top and bottom here. So this is fraction 1's multiple. And we have to do the same thing. We have to say, okay, 60 divided by 15 is 4. So that's fraction 2's multiple. So then we have to come over here and multiply 4 top and bottom. So now we have 25 60ths, and we have 4 60ths. If I found the LCM right, and if I did the division right, and if I did the multiplication right. That was a lot of steps. We're not done yet. What we're going to do next, now we find the add for the 3rd or 4th step, depending on how you're counting, and we get a total of what? 29 60ths. All right. And this is the most common taught algorithm. Let's compare the same problem with the arrow algorithm. 5 over 12 plus 1 over 15. The arrow algorithm says you got to multiply these two together. I don't have a calculator nearby. I could say, okay, what's 15 times 12? So 5 times 2 is 10. Carry the 1, 2, 3, 0, 1, 5. I get 180. So that's my new denominator. 15 times 5 would be 50 plus 25, 75. And then 12 times 1, oh, I got that one. Add them up. 70, 80, 87 over 180. That's not the same as I got before. It must produce, or I screwed up. Let's see, what number goes in the top and bottom here? 3. Yeah, 8 plus 7 is 15, 1 plus 8 is 9, so 3 goes in the top and bottom. So we can divide by 3, divide by 3. Let's see, 3 goes into 8 twice with 2 left over. 3 goes into 27 9 times. 3 goes into 18 6, and then 0. Oh, there it is, 29 over 60. All right, so we've got this bit of work up here to compute the sum, and then we've got this bit of work over here to complete the sum. They're both a lot of work. There's pros and cons. Is finding the LCM easy? Sometimes, depends on the numbers. Yeah, this wasn't too bad. It was a little bit of work, but it wasn't too bad. And then after I found the LCM, I had to do a division and then a multiplication before I could add. Over here, let's see, I just had to multiply, 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 add. I love that. But then I had to do some division. Right? Same kind of steps, just in a kind of different order. So the question is, are you a better multiplier and adder, or you are a better play with numbers to find LCMs and their relationship, multiples and divisors? Okay, 2 different methods.
Which one do you prefer?
I prefer the arrow method, because sometimes I find this to be painful, find the LCM.
Especially on bigger.
And I can multiply pretty quick, in general. Yeah. And reducing, oftentimes I don't care about reducing too much. 87 over 8, 180, that's not getting it, sorry. Reducing is sometimes overrated. All right, so speaking of reducing, let's go to mixed numbers. It really has nothing to do with reducing. And by the way, subtraction is the same algorithm. Doesn't matter whether you add or subtract. Does it?
I was just gonna say, since like most of the time in math, if they give us a mixed number and generally you're supposed to change it to an improper fraction, so why even do we deal with mixed numbers?
Excellent question. Mixed numbers versus improper fractions. And the reason we care about both of them is the idea of communication versus calculation. Okay. So example, let's take 3 1/2, which literally means 3 plus 1/2, means I need a common denominator, which would be 2, right? So 2 times 2, so that gives me 6 plus 1, or 7/2. I'll go over a shorter way to do that. This is what mixed numbers mean. We say it as 3 1/2, which is a literal plus for the end. To add two fractions, you got to find the common denominator. You keep the denominator, you combine the numerators. So 3 1/2 is the same number as 7/2. So I'm going to be running a fundraiser down the road. So could you drive 7/2 miles to this building on Main Street? That sounds weird, right? I would say drive 3 1/2 miles. And you're like, oh yeah, okay, 1, 2, 3, or and then a half. So in communication, we've learned to communicate with mixed numbers. On a number line, they help us find stuff better. Whereas stating something as an improper fraction is, oh shit, 7/2. So I got to go a half, and then another half, and then I can do that 7 times, right? So counting by a fraction is trickier than going whole number plus part. So it really comes down to communication versus calculation. Hang on one second, Sarah. And then the other thing is, it turns out mixed numbers are just a pain in the butt to calculate with. It doesn't matter whether you're adding, subtracting, multiplying, dividing, they're nasty. Why? Because they're mixing addition and division in the same number. Whereas an improper fraction, it's just a very simple fraction. It's just division. So we'll do some examples of calculations with a mixed number versus calculations with an improper fraction. So.
Can't you just do 3 times 2 and add the 1 on top?
Yeah, I mentioned I was going to go over a different method.
Oh, okay.
Yeah, but the bottom line is, why can you do that? So Sarah was saying, if you have 3 1/2, you can just take the 3 times the 2 and then add that result to the top. So 3 times 2 is 6, plus 1 is 7, keep the denominator. That's the shortcut. The question is, why do you do that? And the reason is because you are literally adding fractions that don't have the same denominator. And the common denominator is that sucker right there. So in this class, remember, we want to get good at how and why. Why can we do this?
Because of that.
That's why. Why can we do this? I'll draw you a picture and show you. That's what it boils down to. Concrete, show me. Yep.
So the way that you would model that, you'd have 3 holes.
Yeah, so model, yeah, so if I wanted to model that, right,
What happened?
I would draw it as 1, 2, oops, I'm doing a good job making the same size, 3, and then I need to draw another one so I can show the half of that,
Oh, that, I get it now.
right? See what I'm saying?
3.
So here's my 1, 2, 3 and a half. Now if I go back and I cut them all in half, then I have 1, 2, 3, 4, 5, 6, 7 halves. So that's 3 1/2 versus 7 halves, picture-wise. And really, when I say 3 1/2, right, I have to have a common denominator, which the picture justifies. And also the method that we're all familiar with, where we say, let's take the 3 and multiply it by 2. Why do we do that? Well, every one has to have the same size pieces because a fraction is equal parts of a whole. Those parts all need to be halves. So that's why we have to take 3 times 2. Each of those 3 pieces has to be cut into 2. Then add the extra one on. Right, so the picture shows why that works too. All right, let's do a subtraction problem. First, let's try, let's pick on 7 halves again. So suppose I have 7 halves, and I want to take away from that 4 thirds. So forget about drawing a picture for a minute. We're not going to worry about modeling. We're just going to algorithm this. So my choice would be to use the arrow algorithm. So 2 times 3 is 6. 3 times 7 is 21. 2 times 4 is 8. And what am I doing with these things? Subtracting them. Okay, so 21 minus 8 is 13.
13.
And I'm done. 13, 6 is a lovely number. They have no common divisors. It doesn't reduce. Okay, let's try a similar but different problem. Let's take 3 1/2 and subtract from that 1 1/3. Now, often if you saw this in a book, it would be stacked. It would be written as 3 1/2 minus 1 1/3, which I think is cool, but that's okay. All right, so let's see. I have a half, I need to take away a third. Can't do that in my head. What's the problem?
The denominators.
Yeah, I need a common denominator. So I'm gonna switch colors here. What should the denominator be here? 6, which means we have to multiply by 2, top and bottom. Which is 2, 6, or 3 top and bottom. 3, 6. Okay, now I can do this. So 3, 6 minus 2, 6 is 1/6. 3 minus 1 is 2, so 2 1/6. Wasn't too bad. Either way, I have to find a common denominator. All right, so we're going to do a different one. I'm going to have you try it. New problem, how about 10 thirds minus 3 halves? So do that one first. Color is better. Versus that blue one second. Uh-oh,
You can't subtract 2
I
thirds
can't take 3 from 2.
unless you can have a negative fraction.
You could, but do we want to do that to kids on top of fractions?
No.
Probably not. But we got to borrow.
I don't want to do it to me on top of
So we're going to borrow 1 from the 3.
That
Okay,
becomes
so that's a 2. What does this become then?
12?
No. What did we borrow? A whole. What is a whole here? 6, 6. So this now becomes 6, 7, 8, 6. Ooh, that's different than the way I borrowed before, kind of. But before we were borrowing tenths, or tens. Okay, so now I can do 8 minus 3. But most students are going to write 12 there. And I'm going to write 12 there on a day that I'm not slowing down to think about it. Right? Because that's what I do normally. 8 minus 3 is what, 5?
Oh. I was so confused for a minute there. I was like, why do you keep saying 12? Are you multiplying? And then I realized you're doing the 1 on top of the 2.
Yeah, so you borrow 1 and you would call that 12,
Yeah, like
6,
to me that
right?
wouldn't even occur.
Okay, but like when I do regular
No, I know.
subtraction with whole numbers, that's the way I
Yeah.
would do it, right? So if this were the problem, 32 minus 23, I would have to borrow from that 3 and put a 1 there to call it 12. But that's only because powers of 10.
So,
Yeah.
how do you
Right.
get the 8?
So again, I borrowed here
Do you
1 whole. 1 whole happens to be 6, 6. 6, 6 plus 2, 6 is 8, 6.
Okay.
Yeah.
Got it.
Okay.
I was a little slow.
Which is a royal pain in the bottom. But I do get a nice, mixed number answer. 1 and 5, 6 means the same thing as 11, 6. But it was just harder to get there. So, alternative, don't do this. Rewrite your mixed numbers as improper fractions. You don't have to worry about borrowing fractional parts anymore, which is going to throw a lot of kids into a fit. Right? So the moral of this story is don't calculate with mixed numbers. Can you do it? Sure you can. It's just more challenging. Convert to improperly. And then do your calculation. Wait till you see what this looks like with multiplication. It gets even messier. Forget about division.
Can we?
No, not completely. We can forget about division of mixed numbers, yes, and just do division of improper fractions. It's way easier. Okay, so those are the high points of section 2. We are going to skip on along to our activity. So let me see if I can find, to do the activity, we're going to start off with pattern blocks. Let me find my printout of the activity. It is activity 7 in your workbook. My workbook. Here, chapter 6. All right. The old workbook, so mine's on a different page, but it's the same thing. There we go. Okay. Oh, it's even the same number activity. Okay, so what page is it on? 103. Page 103. So we're going to add and subtract fractions. We're going to use the pattern blocks at first, and then later we're going to switch from one pattern block being a whole to 2 pattern blocks being a whole, and then we're going to try doing the same thing but with fraction strips. And I gave you guys a sheet of fraction strips the other day. There is a page of fraction strips available somewhere on our website on miscellaneous resources, fraction strips. And we can download that fraction strips file. All right, so let's try one of these. I need a new page. And let's look at their first example, which they pretty much do for us. So let me see. First, I need to know what a whole is. So we kind of have to have a key for this. So in my key, I'm just going to make a note that this is one whole at first. So that's one whole for reference. All right, so then we have the trapezoid, we have the rhombus, and we have the triangle. So put those side by side. Or as my grandma used to say, side by each. What's that?
That's what my grandma used to say.
All right, so, so the red appears to be what part of a whole? A half. And the blue appears to be a third. And the green appears to be 1/6, okay? And with the kids, we're gonna say, okay, can you put 3 of these perfectly on top of the hexagon? So we're gonna want the kids to demonstrate that. And whenever possible, we want real toys, not fake toys like these. All right, so those of you at home, there's a link to this on our miscellaneous resources page. Yeah, so 3 of them fits very nice, so I can see the 1/3 aspect of that. And then you could do a similar thing with the triangles and show that 6 of them fit nicely inside that same hexagon. All right, so the next thing we want to do is we want to be able to illustrate, where'd that page go, a red plus a green, or 3 green, excuse me. So we want to show what a half looks like. And that's what I gave you the dot paper for. At first, we're just going to use the actual shapes to build these, but I want you to also try to draw these too. And that's what the dot paper is there. Because I don't know about you, I have a hard time drawing. I don't have a hard enough time drawing a square, never mind a nice hexagon or a trapezoid. The dot paper guides us in that. So let me get my dot paper up here. I've got it here, isometric dot paper. Go to the site and build your own. All right, so let me get a snapshot. This into my page. Hopefully that's enough. All right, so again, I'm going to try and draw a picture of 1/2 plus 3/6. So, wrong page, over here, here we go. So 1/2. First I have to show my whole, and then I've got my half. And then I want to compare that to 3/6. And for that, let's see, will green even show up here? Maybe. So the dot paper is just a nice guide to draw these suckers in there. So now I have 1, 2, 3. And so we just want kids to play around with the toys. So what happens if I put these together? And you can stick them together on top of each other. Let's see. Just do a copy of this. Nope. So draw it in, highlighter, highlighter. So there's my 3/6, and down here is my 1/2. So altogether I have 1 whole. So on the first page, we won't worry about drawing pictures. We'll just worry about playing with them. So what you want to do here is, in this case, we could rewrite each of these as a red plus a red, or 3 greens plus 3 greens, and altogether we can come up with an answer of 6/6 or 1 whole, or 2 halves. Either way works okay. We're going to do a similar thing for this down here. So I want to illustrate it, write it down. So new page. Let me try that again. And then we're just going to keep filling this out. And we'll stop the recording in a moment and let everybody work and ask questions after I illustrate this one. So I need to show a half. Let's grab these guys. So here's my half. And I need to show a third. So let's say, here's my third. So everyone knows what I bargained for. Well, but then I can redraw them as green. So let's just draw over these. So I could also say I have 3 green and 2 green, right? What's 3 green as a fraction?
1/3.
Well, 1 blue as a fraction is 1/3. Yeah, 3 green would be 3/6. And 2 green would be 2/6. So altogether, I could say I have 5 green underneath that, which means I have 5/6. So for now on page 1, you don't have to draw the illustrations, just fill in the worksheet similar to that. On the next part, you're going to do a bunch of drawings on top here. So I'll come back to that in a minute.